Hello everyone. Today, I want to take you on a deep dive into a masterpiece that has fundamentally reshaped how we understand human cognition, thinking fast and slow. Growing up, whether in our daily lives or in rigorous scientific research, we're always assumed or expected to be absolutely rational beings. We naturally believe that when faced with choices, our brain acts like precision computers, automatically weighing the pros and cons, calculating probabilities, and ultimately arriving at the optimal solution. But in reality, when faced with many problems, we often abandon the thinking process because it is difficult, complex, and sometimes even mentally noisy. Instead, we turn to trusting our intuition and relying on widely circulated experiences, regardless of whether they are correct or not. Naturally, this can ultimately lead us to the wrong answer. The greatness of this book lies in how ruthlessly, yet elegantly, it reveals a profound truth. The human brain has never been a perfect, rational calculator. Instead, it is a complex system driven by two entirely different sets of underlying code. The decisions we make every day, which we believe to be carefully considered, are actually largely manipulated by intuitive algorithms that we don't even notice. Today, we're going to conduct a deep code review on the brain to see exactly how this system operates and where the bugs are hidden. First, let's meet the unconventional author behind us, Daniel Kahneman. The scholar on the screen possesses a very unique label. He is a pure psychologist, yet he crossed the disciplinary boundaries to win the Nobel Memorial Prize in Economic Science in 2002. In the academic world, this is an extraordinary level of recognition, indicating that his discoveries fundamentally shook foundations of other disciplines. So, what exactly did he discover? For decades, classical economics and many early decision-making models were built on the foundational assumption: humans are rational economic agents. That is to say, our brains operate like intelligent agents that can perfectly calculate probabilities and relentlessly pursue the maximization of self-utility. But Kahneman's research mercilessly shattered this illusion. Through a massive number of ingenious experiments, he proved that when facing uncertainty, humans simply do not operate like rigorous logic algorithms. On the contrary, to save computational power, our brains heavily rely on heuristics or mental shortcuts. These shortcuts helped us quickly dodge predators in ancient times. But in modern, complex decision-making environments, they generate systematic, predictable cognitive biases. It put humanity down from the pedestal of perfect calculation and restored us to our reality as flawed human beings. This also marked the definitive establishment of behavioral economics as a discipline. Although only Kahneman's name is printed on the cover, the book is actually the product of two minds. In the book, Kahneman repeatedly mentioned his lifelong friend and research partner, Amos Tversky. They had widely different personalities, yet they created a magical chemistry in their academic work, co-publishing a series of disruptive papers. Unfortunately, Amos passed away prematurely from illness in 1996 and couldn't wait for the Nobel Prize. Therefore, thinking fast and slow is to a large extent Kahneman's way of honoring his old friend and a systematic summary of their decades of collaborative research. Before officially introducing the core theory of this book, let's look at a slide on the screen and do two small warm-up tests. First, please look at the face of the woman on the left. When you see her at first glance, a word almost instantly pops into your brain: angry. You don't even have to think deliberately to feel her emotion. This is a form of extremely fast pattern recognition. But what if I told you that this is actually a snapshot of someone just about to sneeze? Once you accept this context, doesn't it seem perfectly reasonable? This example tells us that our incredibly fast, unthinking intuition can sometimes make wrong judgments due to lack of context. Now, let's look at a classic cognitive test on the right. A bat and the ball cost $1.1 in total. The bat cost $1 more than the ball. So, how much does the ball cost? I'm guessing the first answer that popped effortlessly into many of your minds was $0.1, right? 1.1 minus 1 equals 0.1, which feels very intuitive. But if you pause for a moment and engage your logic to verify it, if the ball is $0.1 and the bat is $1 more, the bat would be $1.1. That makes the total $1.2, which is incorrect. So, through rigorous deduction, the correct answer should be the ball is $0.05 and the bat is $1.05. So, through rigorous deduction, the correct answer should be the ball is $0.05 and the bat is $1.05. These two simple examples perfectly demonstrate the two entirely different processing mechanisms that exist in our brains. These two simple examples perfectly demonstrate the two entirely different processing mechanisms that exist in our brains. One is as fast as neural reflex but prone to error. The other is as accurate as a rigorous algorithm, but you have to deliberately wake it up. With that intuitive experience in mind, we now officially enter Kalman's core cognitive architecture, the dual system model. Everyone, please take a look at the comparison chart on the screen. On the left half of the brain, we use warm orange and nodes resembling a neural network to represent System 1, also known as the fast thinking. Its operation is intuition-driven, automatic, unconscious, and highly emotional. Just like recognizing the face earlier, it has extremely rapid response capabilities and consumes almost none of your mental load. When dealing with tasks like pattern recognition, it is an absolute expert. More importantly, System 1 is like a background program that is always online. It is turned on by default, and you cannot shut it off at will. On the right half of the brain, we use calm blue and precision gears to represent System 2, or slow thinking. It is a rational, focused, conscious, logical calculation center. When you were just verifying the specific prices of the bat and the ball, that was System 2 at work. Its characteristics are that it calculates slowly and is extremely demanding of energy and attention. It is exclusively designed to handle complex tasks. Precisely because it is so energy-consuming, System 2 is inherently lazy and remains a low-power standby mode for the vast majority of the time. So, how do these two systems interact in our daily lives? Please look at the relationship diagram at the bottom. System 1 acts like a hardworking, grassroots employee, constantly providing System 2 with initial impressions, intuitions, and default action strategies. If everything goes smoothly, System 2 will simply rubber stamp and adopt System 1's suggestions. But when System 1 encounters an unexpected situation it can't handle, like finding out the $0.1 answer doesn't add up, or when we deliberately scrutinize something, System 2 is awakened to veto System 1's impulses or to engage in deep logical reasoning. Understanding this underlying interactive logic helps us realize that the reason humans commit all sorts of absurd errors in risk decision-making and project evaluation is often due to the laziness of System 2, which allows us to fall defenselessly into the intuitive traps set by System 1. After understanding the speed of System 1, let's look at a slide. How exactly does System 1 react so remarkably fast? The secret lies in the word on the top left of the screen, heuristics, which are the brain's mental shortcuts. Please look at the maze in the bottom of left corner. When System 1 encounters a complex problem, it simply doesn't have the patience to honestly navigate the maze to find the exit. Instead, like the yellow arrow in the image, it directly takes a shortcut and jumps right over it. This core mechanism of taking shortcuts is called attribute substitution in cognitive psychology. Let's look at the classic example on this slide. Suppose you are now facing a very serious decision. Should I invest in this company's stock? To rationally answer this hardcore question, you need to mobilize System 2 to read complex financial reports, conduct deep market research, and build financial valuation models. However, to avoid this intense mental labor, System 1 will quietly replace the question in the background with extremely simple, emotion-driven one. Do I like this company's products? If your answer is yes, your brain will immediately pop up a strong intuition. Buy the stock. This is heuristics using a simple question to substitute and answer a complex one. So, is this built-in algorithm of the brain good or bad? Like the scale in the middle of the screen, we need to weight it objectively. Please look at the green area on the top right. Pros. We must admit that heuristics have a massive evolutionary advantage. First, they provide rapid response and crisis warning. Like the driver in the picture driving in bad weather, when danger suddenly strikes, your System 1 will make you hit the brakes instantly. You don't need to calculate physics equations. Second, it is a powerful tool for cognitive energy conservation. Look at the brain battery icon. System 1 helps us handle 99% of the routine trivia in our daily lives, maintaining our high daily efficiency and preventing the brain from crashing due to computing overload. However, please shift your gaze to the red area on the bottom right. This is exactly the core reason why Kahneman won the Nobel Prize. In modern society, what we face are often no longer wild beasts in the bushes, but extremely complex financial markets and professional scientific research. In these scenarios, the cost of heuristics is tragic. It brings system biases, causing us to make severe probability errors in complex investment or research decisions. At the same time, because it relies too heavily on experience, it easily leads to stereotyping. Even more terrifying is that because the answers provided by System 1 are often extremely fluent and rapid, it makes us completely lose our ability to doubt ourselves, falling into a trap of overconfidence. In conclusion, our brains are born with this underlying code for taking shortcuts. We cannot uninstall it. What we can do is learn to recognize it in critical decision-making moments and force System 2 to take over the steering wheel. On the previous page, we saw how System 1 practically takes shortcuts. At this point, you may ask, since System 1 is so prone to making mistakes, why doesn't System 2, the rational commander-in-chief in our brains, step in and manage it? When explaining these principles of System 2, the book gives us a very harsh answer, because it's too tired and too lazy. Please look at the left side of the slide. The core operating principle of System 2 is the deliberate allocation of attention. Unlike System 1, which can run automatically in the background, it must be forcefully awakened. Kahneman mentions a very famous psychological indicator in the book. When your System 2 is performing complex mental arithmetic, like continuously subtracting 7, your pupils will physically dilate, your heart rate will increase, and your brain will consume a large amount of glucose. This leads to an important concept in psychology: ego depletion. System 2's energy pool is extremely limited. After you force yourself to solve a complex math problem, or after hold back your temper during a meeting. Your mental battery is drained. When that happens, System 2 goes on strike. This dictates its pros and cons. Please look at the right side. First, let's look at the pros on the top. Undoubtedly, System 2 is the light of human rationality. It is the only tool we have to conduct rigorous logical deduction and calculate complex probabilities. It holds the highest level of executive control. When System 1 impulsively wants to sign a terrible agreement, only System 2 can hit the brakes and shout, "Wait, this isn't right." But we must face its fatal cons below. First, it is too slow and extremely energy consuming, which means it can only process one thing at a time. Second, the most fatally, it follows the law of least effort. Because using our brain is too painful, System 2 possesses an innate, extreme laziness. In daily life, as long as System 1 provides an answer that seems plausible, even if it's wrong, System 2 will act like a perfunctory manager and directly rubber stamp in without even looking. Fine, let's do it your way. The classic bat and ball problem from the book is the best proof of this. The answer of $0.1 is so obviously wrong, but because System 2 was too lazy to verify it, we all fell into the trap of intuition. For those of you familiar with deep learning and artificial intelligence, we might be able to understand System 1 even more profoundly. If we translate Kalman's theory into language of AI, human System 1 is, in a sense, a trained, feed-forward neural network. Please look at the first keyword on the right, fast. When a trained neural network performs inference, it is essentially an end-to-end forward pass. It doesn't need to check root dictionaries step by step, nor does it perform complex logical tree searches. Relying on its network weights, it instantly maps the input to the output. This is exactly like System 1's autopilot mode of seeing the face and directly recognizing the emotion. However, please look at the chart on the left of the slide and the striking stamp in the middle, overfitting. We all know that the easiest trap of the neural network to fall into during training is overfitting, when the model forcefully memorizes all the noises and outliers to cater to every data point in the training set. It draws the highly distorted red line shown on the left. The result is that it performs perfectly on the training set, but its generalization ability is a totally disaster when facing new data. The various cognitive biases and mental shortcuts of human System 1 are actually the results of our brain severely overfitting into past experience. Our life experiences are the training data. Because System 1 relies too heavily on this limited, biased historical data, it forms extremely stubborn weights. Since System 1 is like a neural network, one machinism in the AI field corresponds to the slow-moving System 2. Yes, there it is. Please look at the title. It is the large language models or vision language models that we interact with every day, especially when you are executing deep reasoning. Please look at a slowly crawling snail on the far left, and the corresponding bullet point, high latency in low speed. Why is System 2 so slow? Because it cannot directly output an answer end-to-end based on intuition like System 1. When it takes over a task, it's just like when we force a chain of thought in our prompts for an LLM. It must break down a complex problem into sequential steps. First analyze context, then calculate using working memory, then research existing knowledge, and finally reason logically. This multi-step, autoregressive generation process guarantees that it cannot be fast. But slowness comes at a price. Please look at the massive model network in the middle and the hot, severe clusters at the bottom. High computational resources consumption. In computers, complex chain of thought reasoning means burning massive GPU compute and incurring high token generation costs. While in our carbon-based human brains, the high-speed operation of System 2 similarly consumes blood, glucose, and mental energy drastically. It is precisely because compute is too expensive that our brains configure System 2 into an extremely lazy, do not wait unless absolutely necessary mode. At the end of this book, Kalman very frequently admitted that even though he has studied cognitive biases in his entire life, he still falls into the intuitive traps of System 1. Because this is the factory setting of the human brain developed over hundreds of thousands of years, we cannot simply delete it like uninstall a software. What can we do is establish environmental speed bumps. When you're facing major investments or critical project planning, you must realize that your System 2 might be lazy or even running on low battery. Therefore, do not make decisions late at night when you are excited. Introduce the professional vocabulary from this book into your team, so everyone can act as each other's System 2 to catch those anchoring effect and overconfidence bugs. Secondly, and this is what I want to highlight with everyone here, are the implications for future technology. When we are in the lab every day training machine learning models, optimizing the underlying architecture of LLMs, or reasoning how to make systems make smarter decisions in complex environments, Kalman's dual system theory might offer some inspiration and reflection. The future breakthrough might just be how to perfectly replicate this mechanism of the brain, developing AI agents capable of self-monitoring, agents that can rely on low-power System 1 to output a top speed of 95% of routine tasks, but precisely trigger a highly expensive logical System 2 network when encountering uncertainty and logical contradictions. From understanding human irrationality to constructing machine rationality. This is the entirely new value that thinking fast and slow grants us in this area. Thank you for your time, and I hope it has brought you some inspiration.